In the last class, we discussed special theory of relativity. In particular, we saw that the correct transformation equation between, we didn't actually go to the consequences, but we saw that the correct transformation equations have to be delta x prime. This correct transformation between coordinates, all right? We'll write it in differential form because that's easier to solve problems. Because the transformations are linear, you just substitute x by delta x and t by delta t, you get the correct equations for what do you say, the differentials. Okay, so delta x prime is equal to gamma delta x minus v delta t. Okay, delta y prime equal to delta y, nothing particularly interesting. Delta z prime equal to delta z, and delta t prime is equal to gamma delta t minus v by c square delta x. Okay, so we'll use this thing. So as the first problem, let's find, so if this is how the coordinates transform, if this is the way in which the coordinates transform, let's check how the velocities transform, right? Transformation of velocities. In the case of Galileo, we knew that the velocity, you just need to add the velocities or subtract the velocities depending on the direction. Okay. In this case, this transformation of velocity, you can just find it by, you know that ux is equal to dx by dt, right? That's in the S frame or the unprimed frame, the frame that we call the unprimed frame, right? Correspondingly, in the primed frame, right, ux prime is equal to, we can say dx prime divided by, so when it travels a distance dx prime, it will have, the time elapsed would be dt prime. Okay, but we know from here that dx prime is equal to, so we'll just write this as that's equal to gamma dx minus v dt, right? So you just take the differentials instead of delta, you take d, that's all, divided by dt prime is gamma dt minus v by c square delta x. Okay, so this gamma will get cancelled, right? And you can take this dt outside, so this becomes if you take dt outside from here, okay, that gamma will get cancelled, right? Dt dx by dt minus v divided by, here also you put this dt outside. Okay, so that becomes 1 minus, so it's d here. Okay, v by c square dx by dt, but dx by dt is already ux, right? So this becomes dt, sorry, this is dt and dt gets cancelled, so you have ux minus v divided by, v is the speed of the frame, right? The relative speed of the frame, ux minus v divided by 1 minus uxv by c square, right? So this is ux prime. You see that, okay, so this is easy to remember in the sense that if you had Galilean transformation rule, it would be simply ux minus v. Okay, if it was Galilean transformation, it would be just ux minus v, all right? But when you go to Einstein, okay, this is known as Einstein rule for addition of velocities. When you go to Einstein, you have got this extra factor, all right? And this you can consider as the relativistic correction. Okay? So your intuition will still work, right? If you have if you have a situation, you can think in a Galilean manner and realize what the result, what the relative speed is, right? You have to decide what the relative speed is. Okay, and then you will have to just put in this extra factor corresponding to the relativistic correction, right? So you don't have to do it completely without having any physical idea, right? If it's Galilean, if the Galilean, Okay, so if it is Galilean, right, if it's Galilean, it's ux minus v. If it is Einstein, you have this extra factor. So it's good. This Galilean thing is not completely useless. You can think about it. It has some physical content, right? Also, you have to remember that when v is less than c, this should go to the Galilean rule for addition of velocities, all right? So this is easy. If it's a minus here, it's a minus here also. If it's a plus here, it's a plus here also, all right? Okay, that's Einstein's rule for addition of velocities. Okay, all right. Now this is about relative velocity. Now this is about relative velocity. Okay, and you can write it in this way, right? So for example, we can. It's more. It's more useful to write it in this way, at least in some points. So the physical meaning is clear. What we mean by this, right? Let A be the particle. Okay, let's call A the particle. All right. B, it's the frame S. It's a frame S. It could be anything. It could be another particle. It could be anything. All right. That's the frame S. And let's call C. It's the frame S prime. All right. Okay. And what do you call U? Okay. U is actually the velocity of the particle with respect to a frame S. All right. So we can write it as V A B, right? Velocity of the particle with respect to B. Okay. So the velocity of particle with respect to the frame B. Okay. This is nice because when we have said that there is no absolute meaning for velocity. Whenever you say about velocity, you have to talk about with respect to what, right? So VAB, we can write U as VAB. Okay. And suppose U prime is the velocity of the same particle with respect to S prime. So we can write it as VAC, right? It's velocity of the particle A with respect to the frame C, or with respect to C. Okay. And let's say the velocity in this case, right? This V here. Let's say this is equal to minus VBC. Okay, minus VBC means this is equal to VCB. Right? What does this mean? What does this mean? This means that this is the speed of B with respect to C. Okay, minus of it. Or it's the speed of C, or velocity of C with respect to B. Right? So you see that when you interchange this, you get a minus sign, because when you talk about velocity of A with respect to C. Okay, suppose this is particle A, and with respect to C. Okay, velocity of A with respect to C. Okay, let's say it's equal to velocity of A with respect to C is equal to minus velocity of C with respect to A. All right, you will see that. Yes. Okay. Right, so it's easy to remember. That's what I've used here. The velocity of B with respect to C is minus the velocity of C with respect to B. Right? Then we get this in a nice addition form. We can write this as VAC. All right, velocity of A with respect to C. This is easy to see. Is equal to VAB, velocity of A with respect to B. All right, so we are talking about, we know the velocity with respect to B, and we are asked to find the velocity of A with respect to C. Right, so it's the velocity of A with respect to B plus the velocity of C with respect to B, right? Because the frame C itself is moving with respect to B, divided by the Einstein factor would be 1 plus VAB VBC by C square, right? VAB VBC by C square, because it's UX is VAB, that's VBC. Right, so this is an easy way to remember. You see, VAC, velocity of A with respect to C. This is also Galilean, right? It's velocity of A with respect to B plus velocity of C with respect to B, right? So it's the velocity of the particle with respect to the frame B plus the velocity of the new frame itself with respect to B. In this case, the velocity, the frame C is moving with respect to B in the positive direction, all right? So this may be an easier way to remember it. So you don't need any prime or something. You just think about relative velocity. You don't have to worry whether it's inverse Lorentz transformation or transformation, Lorentz transformation, whether to put prime or something. Right? Okay. All right. So this we can use to solve problems. Can use this to solve problems. And there's a nice thing about this. We have been saying that the speed of light is a constant. Okay. So let's say that the one of these speeds, right? VAB is equal to C. Let's suppose VAB is equal to C. Okay. The velocity of the, let's say, photon with respect to B is C. Now, what's the velocity of A with respect to C? This is equal to VAB C plus VCB, okay, divided by 1 plus VAB is again C, right? VAB is again C, and okay, I think VAC. Sorry, this is, we put it a minus sign, right? So it's VBC. Okay, so this is VBC. Okay, and this would be C VBC by C square. All right, so you see that this is equal to C plus VBC by, so this is equal to C, right? C plus VBC by C plus VBC by C, right? That's equal to C. Okay, you see that the speed of light does not change. The speed of light does not change according to Einstein's rule for velocity addition. Okay, so it's nice because we have all right, it's all consistent. We could have derived the Lorentz transformation equations beginning with the condition that the speed of light is a constant. All right. Okay. And yeah, so this means that if you have a light beam C, all right, traveling with C with respect to the ground, all right, and you are traveling at a speed V parallel to it, even if you measure the speed of light from your frame, Galileo says that you would get C minus V, but Einstein says that you still get back C. Okay, so you can say that that's the property of, that's because of the underlying geometry of space-time, which we'll see soon. All right, we'll be seeing the geometry soon. Right. So one thing you have to remember is that there's nothing special about light here. Okay, there's nothing special about light here. Okay, we'll see. I'll make this more explicit. You should remember that there is nothing special about light. Okay, what's important is that our space-time, okay, our space-time admits an invariant speed. There's an invariant speed corresponding to our space-time. Okay, and light in vacuum happens to travel at that speed. Okay, that's the way we identified it. Okay, light happens to travel at this speed in vacuum. All right, light happens to travel at this speed in vacuum. Right. So this number C is important. Right. In SI units, this would be about 3 into 10 raised to 8 meter per second. All right. This number is important, not the fact that light is traveling. This number is important. All right. Now, if this was the geometry of space-time, even if light did not travel at this speed, we still would have special theory of relativity. That still would be correct. All right. It's a lucky coincidence. It's a lucky thing that light actually travels at this invariant speed. So this helped us to understand this helped us to understand the, yeah, what do you say, the geometry of space-time. Okay, so you have to remember that. So because in a medium, for example, in a medium, light travels at a smaller speed. Okay, you know that in a medium, light travels at a lower speed than this. Okay, because of the refractive index. All right, because of the refractive index. All right, but even then, the same equations of special theory of relativity will be valid. You don't have to substitute for another C or something. Right? So it's not important because it's the speed of light. It's important because it's an invariant speed, or it's a universal constant associated with our space-time. All right. Okay. So the physical property of light, it doesn't matter. The effects of relativity is not because of the physical properties of light. Light just happens to travel at this speed. Okay. All right. Yes, I think I am sorry for mixing it up. I'll just write it again. This is the VAC is equal to VAB plus VBC divided by Okay, 1 plus VAB VBC by C square, right? So the velocity of A with respect to C, okay, is equal to velocity. This is because we chose V is equal to minus VCB, and minus VCB wrote it as VBC, right? That's what we used. But from the given situation, it should be clear which formula to use. Right? From the given situation, you should understand which formula to use. You don't have to remember this absolutely like this. Right? You don't have to really memorize it in this way. You just remember that, okay, if you have a speed, there will be a speed of the frame. This should be added or subtracted depending on the situation. And correspondingly, you will have 1 uv by c square. All right. Okay, this is the thing you need to remember. You need to put addition or subtraction depending on the situation. If it's a minus here, it's a minus here. If it's a plus here, it's a plus here also. Okay. All right. So that's Einstein rule for velocity addition. We also saw that the speed of light is invariant. Okay, but that's not all. Oh, just write the Lorentz transformation again. I didn't want to remove it. Minus V delta t. All right. Delta y prime is equal to delta y. Delta z prime is equal to delta z. Delta t prime is equal to gamma delta t minus v by c square delta x, right? But that's not all. We'll see that there's a velocity addition rule for transverse velocities also, right? Because of the Lorentz transformation. This is something new. This is something new for Lorentz transformation. Right? This case, it is, you can think of, all right, it looks very much like the Galilean transformation. It just have this extra factor. In the case of transverse velocities, okay, you have to be more careful, and you have to remember this. People usually make this mistake to assume, because delta y prime equal to delta y, people tend to assume that delta u prime, u prime, uy prime is equal to uy, but this is not true. All right. In Galilean case, that's true, but here it's not true. Okay. That's because time has a non-trivial transformation. Okay. So let's look at uy prime. Okay. This you have to remember. Okay. It's or you can remember, you can just get it from the Lorentz transformation. So uy prime is equal to uy. Okay, you just do this. Should I do this? All right, let's say uy is equal to delta y by delta t. All right, correspondingly uy prime would be delta d. Let's put d. Okay, dy prime by dt. All right, dt prime. Right, dy prime is dy, no problem. But dt prime changes to this thing. All right, so it's gamma dt minus v by c square dx. Okay. All right. So you can take this dt outside. So this becomes dy by gamma dt into 1 minus v by c square dx by dt. All right. You remember this is dx by dt, right? Remember that this is dx by dt because we are assuming that the frame is moving along the x direction. All right. So you shouldn't confuse between this. Okay. So this becomes dy by dt. If you take this, dy by dt is simply uy, no problem. All right. Gamma 1 minus. All right. What's dx by dt?
ux.
Yeah, dx by dt is ux. So this becomes uxv. Remember that v is the speed of the frame, right? Okay, uy by gamma 1 minus uxv by c square. We know that we can write it in a different form. If we can remember it in terms of gamma, you remember it in terms of gamma, or it's 1 by gamma is square root of 1 minus v square by c square. So you can also write this as uy multiplied by 1 minus v square by c square divided by 1 minus uxv by c square. Right? Remember, you see that this factor is still uxv by c square. Right? So there are all sorts of velocities here. There's uy, you have got v, and you have got ux in this formula. Right? Similarly, you can find it for z also. Right? uz prime, you will say it's equal to uz square root of 1 minus v square by c square 1 minus uxv by c square. This factor is the same. Okay. So you have to remember that. Right? Okay. Now let's do more problems. Okay. Now, usually we can go to the consequences of this. We haven't really looked at the physics of what this Lorentz transformation means or the physical consequences of it. Okay, but these Lorentz transformations themselves are really important. So we'll do some problems in Lorentz transformation, but just mathematically, we know that these are such transformations are there. So we'll do some problems just using this mathematical formula, and then we'll see some of the examples there. Then we'll go into three specific consequences. All right, simultaneity, that would be in the next class, I hope. Okay, simultaneity, time dilation. There are so many different ways to derive these things. All right. And length contraction. Okay. Now we can, you know that these are consequences of the fact that there is a fundamental constant speed. Okay. And the Lorentz transformation can be seen as the transformations that leave this particular speed invariant. So you can derive this from the Lorentz transformations, or you can obtain this from the physical arguments, all right, just by assuming that speed of light is the constant. So if you look at Griffiths, Electrodynamics by Griffiths, there's a chapter on relativity. It's all the arguments are given geometrically, just by assuming that the speed of light is a constant. He just takes it as a postulate and derives all this, right? But we'll do it a bit more abstract manner, because these things I hope you're familiar with. So we'll just obtain these results from the Lorentz transformations themselves. Okay. Before that, let's do a few problems using Lorentz transformation. There are problems being asked using which you can solve using Lorentz transformation. Again, I remove this, so delta x. Again, delta t prime is equal to gamma delta t minus b by c square delta x. Okay, so let's do a problem. This we'll see and there are problems on all these things. Okay, we'll do problems, and after doing this, we'll go into a geometrical formulation of special theory of relativity known as Minkowski space. Okay, there are problems being asked even from there. Okay, so because all these things are actually in your syllabus. Okay, all these things exist in your syllabus. Either in classical mechanics or in electrodynamics. So these things are there in your syllabus, right? So even the geometric formulation. Earlier, they didn't really ask questions from the geometry part, from Minkowski geometry part, but nowadays they ask questions from there. Okay. All right. And but it's actually much easier to think about special relativity using geometry than using these things, all right? But we'll see these things. We'll first discuss these things and then go to geometry and see that when you look at the geometry, all these things can be seen as a consequence of the geometry of space-time. Okay. So the first problem that we are going to discuss is this. Okay. In an inertial frame S, an event takes place at, this was actually asked, I think, an event takes place as, or a similar question was asked. Event takes place at 200, 0, 0. That's a spatial, okay? And 2 into 10 raised to minus 6 seconds later. Okay, 2 into 10 raised to minus 6 seconds later, another event takes place at 1000, 0, 0. This is asked for a previous net question. Okay, so immediately see that they have given 3 spatial coordinates. All right, and there's no change in the x, y or z directions. It changes the event. All right, the separation. But these are 2 events. Okay, what do we mean by events? At this point, you just know that events. If you take tx plane, an event is a point in this. This is known as space-time. Okay, this is known as space-time. An event is a point in this space-time. Right? This actually, there should be x, y, and z. We suppress all the others. All right. Okay, we can actually draw 2 of them, x and y, if you like, and t. Okay, so if you give t, x, y, z, it's known as an event. Right? If you give all 4 coordinates, it's known as event. Okay, so when you say there's an event, it need not be anything dramatic. It's just a point in this space-time. An event is just a point in space-time, and all points are events. Right? All points in this space-time are events. Okay, all points. The name of these points are called as events. All right. So when you say event, what comes to your mind is something dramatic like a bomb explosion or something. But in physics, okay, bomb explosion is an event in this sense. But when in relativity, it's more general. Right? It need not be a bomb explosion. It's just a point in space-time. Right? That's known as an event. All right. Even if nothing is happening, a simple point is called an event. It's just a name. Right? That's what we mean by event. All right. So event takes place at this point and at this point, all right? So yeah, we don't have to really draw it at this point. Okay, it's this, I just wanted to explain the term event. Right? Find the magnitude and direction of velocity of frame S prime in which these events appear simultaneously. Okay, find the magnitude and direction of velocity of a frame S prime in which these events occur simultaneously. Right? So the thing is that they have given us two frames. They have given us two frames, and they have said that in this frame, let's call this as S frame. In this frame, these events are separated, okay, spatially separated by 800, right? 1000 minus 200, 800. Okay, and it happens in this frame. It happens 2 multiplied by 10 raised to minus 6 seconds. So in the S frame, okay, let's do the solution here. We know this in the frame S, these things are given. Delta X, okay, the spatial separation between these two events is equal to simply 800. Right? Maybe it's meters, 800 meters. Okay. All right. And delta T, it happens, these events, or these two things take place, or these two events are separated by 2 multiplied by 10 raised to minus 6 seconds. So delta T is equal to 2 multiplied by 10 raised to minus 6 seconds. They have given S prime. Okay, we know that delta T prime is given to be 0. It happens simultaneously in the frame S prime. It happens simultaneously in the frame S prime. So what's the velocity? What's the velocity at which S prime travels with respect to S? That's the question. So how do we find this? Okay, so let's write down this formula. We know that delta prime is equal to gamma delta T minus V by C square delta X. All right, and you just substitute these things. Delta prime is given to be 0. 0 is equal to gamma. What's delta T? Delta T is given to be 2 multiplied by 10 raised to minus 6 minus V by C square. All right, we don't know V, so it's V by C square delta X. Delta X is 800. Okay, now we just solve for V. Right, just solve for V. So how do we solve for V? Okay, so this gamma is gone. So you see that 0 is equal to 2 into 10 raised to minus 6. Just take the LCM, right? C square minus V 800 divided by C square. Am I right? Yeah, I think that's correct.
V by C square 800 is equal to 2 into 10 raised to minus 6.
Yeah, all right. If you think that's better. Okay, let's do that. So V by C square, this gamma. Okay, this is a 0 here, so this gamma doesn't change anything. This term has to be 0, right? So V by C square 800 is equal to T into 10 raised 2 into 10 raised to minus 6, right? So from here we see that V is equal to 2 into 10 raised to minus 6 C square divided by 800. Is that correct?
Yes.
No, I think it's V by C, right? It's V by C here. It has to be V by C here. Sorry, right? Shirele. V by C alle. Transformation V by C square or no?
V by C square and
yeah, the dimensions are checkable. So there's a C square here. I think I made a mistake in my notes. Okay. Sorry. All right, so that's correct. You just solve this and you'll get the answer. Okay. So what would be the answer? We can just solve it. I think it's easily done. 2 into 10 raised to minus 6. 3 C square is 9 into 10 raised to 3 into 10 raised to, so it's 9 to 10 raised to 16, am I right? Divided by 800. Okay, so that's equal to, is it easily done? 2 into 9. I think we can write it, right? So the options, right? Sometimes the options are given in terms of fractions of C, right? Sometimes the options are given in terms of fractions of C, right? So at what fraction of the velocity of C does it move? So you can just write it as multiplied by C, okay? So this would be 2 into 10 raised to minus 6 into 3 into 10 raised to 8 divided by 800 C, okay? So now that's much more easy. You see that this is 10 raised to 2. So it's 6 by 8C, right? 6 by 8C, or it is 3 by 4C. It's 3 by 4C. Okay. So usually the options, okay, it depends. Sometimes they give it in a multiplied way. Usually, but the options are given as fractions of C. What fraction of C is the velocity? Okay. So you see that it's 75% the speed of light. Okay. In this case, the option was given in terms of C. So you better not multiply one C. Just leave this C here and then calculate it. All right. Okay, so that's how you do it. You have to be careful. Okay, so yeah. All right. Okay, let's do another one. This also, I think, was asked. Such questions are being asked on this. Okay, two events separated by a spatial distance. I'll just write it down. Delta x equal to 3 into 10 raised to 9 meter are simultaneous in one inertial frame. Okay, so delta t is equal to 0, simultaneous in one inertial frame. So you see, okay, we already see this result here. The events which are simultaneous in one frame are not simultaneous in another frame, right? So if I say that two things happened at the same time, another observer can disagree and say that no, these two things cannot have happened at the same time. Okay, so we already see. We'll do this in a bit more formal. You see that simultaneity is relative. Okay, so actually not only simultaneity is relative. Okay, some of the events, okay, the time ordering is also relative. We'll see that for some events, the time ordering is also relative. I may say that X happened after Y, but you may say that X happened before Y. Okay, this is not true for all pairs of events, but for some events. Okay, for some events, and simultaneity is relative. Right? So that's again the thing that we are going to see here. Find the time interval between these two events in an inertial frame moving with a constant speed. V is equal to 0.6 C. All right. So they have, in this case, they have given the V, and you need to find delta T prime. Okay. So you just do this. It's easy. You just use the Lorentz transformation formula in a differential form. Delta T prime is equal to delta T minus delta x V by C square divided by square root of 1 minus V square by C square. Right? That's it. We have got all the things that we need to do. So delta T is 0. So this is minus. Okay? And delta X is given by 3 into 10 raised to 9. Okay. And V is 0.6 C divided by C square and divided by square root of 1 minus B square by C square. Okay, so that's 0.6 C square by C square. It's 1 minus 0.36. Okay, and this becomes okay. And you see that these things can be cancelled easily. Okay, because you are asked about the time, you need to find in seconds. This 3 into 10 raised to 9 and this 3 into 10 raised to 8. Okay, 3 into 10 raised to 8. So that becomes just 10. So that becomes simply 6. 10 multiplied by 0.6 is 6. And here you've got 1 minus square root of 1 minus 0.36. That's square root of 0.64. All right, that's 0.8. Am I right? Is that correct? Yeah. So what is this? You can divide by 2. So it's basically 60 by 8, right? Right. So you can say this is equal to 15 by, you just divide by 4. 2. That's equal to 7.5 seconds. Okay, 7.5 seconds. There's a minus here because we are talking about the time difference. We are talking about the time difference. Okay, so this tells us, this minus says that if this minus actually tells us which event happened earlier. That's all. But you are just asked delta t prime, so it is 7.5 seconds. Right, 7.5 seconds. Now, because this is not given, all right, in which direction? The direction of this velocity is not given. Okay, moving with a constant speed 0.6. That's all what is given. Right. So the answer, you have to choose the correct answer from the option, because if it had given the direction, you could have decided whether it's a minus or a plus. Okay, in this case, it could be even a plus. Doesn't matter. Okay, it could even be a plus. So you then the result will slightly change. Okay, so this is not plus. This is always minus. Right? This is the gamma factor. Sorry, this is the gamma factor. Okay, then you would get a plus here. That's all. Okay, that plus or minus comes because you're talking about delta t prime. It's t1 minus t2, or t1 prime minus t2 prime, or t2 prime minus t1 prime. So it depends on which event takes place earlier. So you look at the options and write down the correct answer. Okay. So since the direction of velocity is not given, the direction of the speed is not given, this doesn't really matter. Okay, the sign does not really matter. It could be anything. It could be minus or plus. Okay. We'll do one more example. Velocities at an angle. Velocities at an angle. Yes, you will use the velocity addition rule here. Okay. So the question is this: if V1 and V2, if V1 and V2 are the speeds of two particles in the laboratory frame, these are speed of two particles in laboratory frame. Okay. And theta, the angle between their directions. Theta is the angle between the directions. Angle. Okay, between V1 and V2 as observed from the lab frame. Okay, calculate the velocity V2 with respect to a particle with velocity V1. Right. So when you look at this from the lab, this is V1 and this is V2, and this angle is theta. This angle is theta. All right. So if you now you need to calculate the velocity of this particle 2. Okay, particle 2. This 2 we call it as particle 2, and this is particle 1. So what's the velocity of particle 2 with respect to particle 1? What's the velocity of particle 2 with respect to particle 1? Okay. So we know that there's a different transformation rule for velocity in the longitude direction and in the transverse direction. So you have to just take this into components and use the velocity addition rule. Okay. So direction of velocities are given like this. So it should be, you can be a bit careful. Okay. So we can write V2. Okay. V2. We take this along the x direction. Doesn't matter. The particle 1 we can say moves with respect to our x direction. Okay. There's no, you don't lose anything by assuming that. Right. So the x component of V2. X component of V2 is V2 cos theta. Am I right? Yes. Similarly, the y component of V2, there's no z component, right? Y component of V2 is V2 sin theta, okay? Because this V2, this velocity can be written as resultant of two vectors, right? One is V2 sin theta and the other one is V2 cos theta. Okay. And we have got yeah, this is in our frame, right? This is in our frame, right? But we are talking about what are these velocities with respect to this frame V1? What are these velocities with respect to this frame V1? Okay, what happens? Should we subtract or add? Should we add or subtract V1 to this to find the x component? Should we add or subtract this? So we can write it as V2 x prime. What is this prime? This means that this is the velocity with respect to or x component of velocity. Okay, x component of velocity with respect to particle 1. Okay, what is this? What is this? This is the x component of the velocity with respect to a lab. Okay, this is the x component of velocity of particle with respect to a laboratory. Okay, because we have taken this as our x-axis. Okay, and this is the y component of the velocity with respect to the lab frame. All right. Now we need to find the corresponding velocities with respect to particle one. With respect to particle one. All right. So I'll just write it here. V2x is equal to, we know that either we have to add or subtract, right? So it's V2x, and what is here? It's add or subtract, we'll fix it. V1 divided by, again it's add or subtract, okay? And then this is the velocity of the frame, all right? This is the velocity of the frame. So you will have V1, V2, x by c square, right? This is the x component because it's x component here, right? Now you tell me whether it's addition or subtraction. Should I put a plus there or a minus there? Can you answer? You should look at the situation and think it in a Galilean way and decide whether to put a plus or a minus there. What would be your answer? Anything? So you remember that this is the x component of, yes?
അതായത് V2 cos theta ആയതുകൊണ്ട് രണ്ടും ഒരേ ഡയറക്ഷനിലായതുകൊണ്ട് മൈനസ് വരൂലേ?
Yes, correct. All right. So this is V2 cos theta. You're talking, this is V2 cos theta, direction of V2 cos theta. Okay. But this is with respect to lab. This is with respect to the laboratory, right? And you are actually traveling parallel to it with the velocity V1 and looking at the speed, right? So the speed should be reduced. Am I right? The speed should be reduced because you're traveling parallel to it. Yeah. So yeah, I think that's rather obvious, right? You don't need the bus, car example, etc. I think that's rather obvious. Okay. Is that clear? So it is a minus here, then it's a minus there. Okay? So you have to always remember to be careful about this sign. You shouldn't miss the sign. Okay, this sign can be fixed just by thinking about it physically. All right. You don't have to worry whether you use a Lorentz transformation or an inverse Lorentz transformation. You just look at the situation. All right. You see that. I'll repeat. You see that this is the direction of V2 cos theta. Okay, this is the direction of V2 cos theta, and this is the direction of V1. Okay, and you are asking, you say that V2 cos theta is with respect to the ground. Okay, V1 is with respect to the ground. So what is the velocity? What would be this velocity with respect to this particle? Right? You said you are already traveling parallel to this in a speed. So what you see would be a difference of these speeds, right? So that's a minus sign. Good. Okay. We've got V2x prime, all right, and yeah. What about V2y prime? V2y prime. Okay. What is V2y prime? Okay, we can also write this. We already have this component, so we can write this as V2x prime is equal to V2x is simply V2 cos theta. This is minus V1 divided by 1 minus V1 V2 cos theta divided by c square. That's V2x prime. All right. What's V2y prime? Okay. Vz is 0, right? You don't have, we are talking about a plane. So Vz is 0. Vz prime is also 0. What's V2y prime? V2y prime, you have to use the rule for transverse velocity. Okay. You'll see that it's equal to V2 sine theta. Okay. Because this is Vy, V2 sine theta, right? V2y, V2 sine theta. Okay. And you'll have this gamma factor, inverse of the gamma factor, 1 minus V1 square by c square, 1 minus V1 square by c square, divided by, as I said, you will have exactly the same factor here, right? You will have exactly the same factor here also, 1 minus V1 V2 cos theta by c square. Okay. I had told you that when we were discussing the transverse velocity addition rule, the factor appearing is exactly the same. Okay. Okay, so now the difficult part is over. We just identified v2x prime and v2y prime. We just need to square and add, right? That would be the magnitude of the velocity, right? So resultant velocity, we'll call it as v2 prime. The resultant velocity is equal to resultant. Okay, that's equal to square root of v2 x prime plus v2 y prime square. Okay, there are so many indices there, but okay, all right, that's square. So you just square and add them. So it's equal to v2 cos theta minus v1 square, this term square. Okay, plus v2, it's v2 square sine square theta, okay, 1 minus v1 square by c square, okay, and divided by, you see that the factors are the same, so it is just there's a square root there, so square root. Okay, so this, when you multiply, when you square, it's a square there, it's a square there, but you can pull it out of the square root and you'll have 1 minus v1 v2 cos theta divided by c square. All right, now it's a matter of simplifying this and you will get just, all right, cos square theta plus sine square theta is equal to 1, etc. You simplify this and you see that you'll get v2, we'll call it as v21. All right, now we'll call this as v21. It's the velocity of particle 2 with respect to particle 1. Velocity of particle 2 with respect to particle 1 is equal to square root of v1 square plus v2 square minus 2v1 v2 cos theta. Okay, you can check this as a homework. And minus v1 square v2 square sine square theta divided by c square and whole divided by 1 minus v1 v2 cos theta by c square. Okay, now if you can remember this, you just remember, right? I don't think they will ask a problem using this formula, but this is a formula. Okay, they may ask it as an optional question. What would be the velocity? Or even if it's asked in an optional way, you know how to do this. Right? They may invert the velocity, direction of the velocities and then ask. So you have to be careful with the signs. Okay, so it's important that you know how to solve this problem. And sometimes in a problem they'll give this angle, right? But then it may be easier to simply do the problem by itself. This is a general formula for this. If the velocities are inclined at an angle, right, then you can do this. Okay. Okay, I'll do one more problem and then stop. There are many problems of a similar, using a similar, in a similar manner to what we have done here. I think I'll just put them as exercises in your notes. Okay, with no new physical content, you do exactly the same thing, right? So here is a question: a pion moving at the speed 0.6 c, a pion moving at the speed 0.6 c emits a muon in the same direction, The speed of muon in the rest frame of pion is 0.4 c. Okay, the speed of muon in the rest frame of pion is 0.4 c. Calculate the speed of muon in the lab frame, right? Calculate the speed of muon in lab frame. Okay, it seems a bit tricky, but you need to understand. If they ask in this way, you need to understand. Okay? So let's just make it more clear by assigning some index here. A pion is moving at the speed 0.6 c. Right? They haven't said, but it means that it's the laboratory. Right? If they haven't said anything, it's the laboratory. So you've got a pion moving at the speed 0.6 c. So that's in the lab. So we can write the velocity of pion. Let's write it as. Okay, let's write it as velocity of pion, okay, with respect to the lab. Velocity of the pion with respect to the lab is equal to 0.6 c. 0.6 c. Okay, 0.6 c. That's what they have given. The velocity of the pion with respect to the laboratory is 0.6 c. And what else have they given? They have given the velocity of the muon, okay, with respect to the in the rest frame of pion. In the rest frame of pion, that means you are going to a frame in which this pion is at rest. Okay, in other words, you are attaching a reference frame to this pion. You are attaching a reference frame to this pion. Okay, this pion is moving at 0.6 c with respect to laboratory. This is the laboratory. Okay, with respect to laboratory, it's moving at 0.6 c. Okay, they are asking, and then you have got a muon. Okay, we have got a muon which is traveling at 0.4 c. Okay, in this 0.4 c is the velocity as observed from a reference frame which is attached on this pion. All right, that's the reference frame in which the pion is at rest. Okay, you are going to a frame in which pion is at rest. In other words, you are going to a frame which is moving at 0.6 c. You're going to a frame which is moving at a speed 0.6 c and observing the pion. So now in this frame, the pion is at rest. In this frame, the pion is at rest because they are moving at the same speed in the same direction. Okay, and what would be the, this is the frame, all right? And what would be the speed of this muon? And in this frame, the speed of muon is given. So what's the speed of this muon in the laboratory frame? That's the question. I hope it's clear. Is it clear? Okay. So we'll write it like this. The velocity of muon in the pion frame. Okay, we'll write this frame as pion frame. It's equal to 0.4 c with respect to the pion. Right? All right. Now what would be the velocity in the laboratory frame? What would be the velocity in the laboratory frame? Okay, should we add or subtract? Should we add or subtract? Right, see, I think it's rather easy to understand. See, if you look at this, okay, so let's think about it again. You have got a pion moving at 0.6 c, okay, and you have got a muon moving at 0.4 c with respect to this pion, okay, with respect to this pion, all right. Okay, so you are looking at it from the lab. So what's the speed of this with respect to the lab? Right now, this 0.4 c is the speed that you measure by moving parallel to it at 0.6 c. That 0.4 c is the speed that you measure by moving parallel to it at 0.6 c. Okay, so what do you expect in the lab frame? Should it increase or decrease? Should it increase or decrease in the laboratory frame?
Decrease.
Decrease. So you're saying you should do 0.6 c minus 0.4 c. Is that what you're saying?
Yes.
Why?
ഇത് ഈ ഫ്രെയിമിന് മൂവ്മെന്റ് ഇല്ലല്ലോ.
ഏത് ഫ്രെയിം?
ലാബ് ഫ്രെയിം സ്റ്റേഷനറി അല്ലേ?
ലാബ് ഫ്രെയിം നമ്മൾ നിൽക്കുന്ന ഫ്രെയിമാണ്. ലാബറട്ടറി ഫ്രെയിം is our frame.
0.6 0.4.
So we have got two frames. Okay, one is the laboratory frame, and the other one is the other one. We'll just draw two things. Okay, one is the laboratory frame. I call it as L. The other one is the pion frame, which moves at 0.6 c. All right. Is that clear?
Frame alle move cheyana.
Yeah, this and from this frame, right? In this frame, the speed is 0.4 c. With respect to this frame.
അപ്പൊ നമ്മുടെ എസ്കലേറ്റർ മൂവ് ചെയ്യുന്നു, അപ്പൊ ആഡ് ചെയ്യണം.
Yeah, you have to add. Right, you have to add because see, you can imagine like, so there's a train, okay, and there's a person moving with respect to the train. Okay, we say that the speed of the person with respect to the train is, let's say, 5 meters per second, but the speed of the train itself is 10 kilometers per second. Okay, so what would be the speed of this person with respect to ground? It would be just the addition of this, right?
Yes.
This is in the train frame, this is in the ground. So you have to add them, right? So if you understand this, you shouldn't make this mistake. Okay, you have to be very careful whether to put a plus or a minus there. So it's 0.4 c plus 0.6 c divided by, now you know that it's 1 plus v1 v2 by c square. So it becomes 0.24. Okay, and you see that this is about 25 by 31 c. Okay, you can see that it's c divided by 1.24. It's 25 by 31 c, because this is given in the option. Okay, you may get this as 1.24, 1 by c by 1.24, Okay, and you look at the options, and they may give it as a fraction like this, as a fraction of two whole numbers. So you just have to divide it and check, okay, whether it comes close to your answer. Okay, that's how you do it. All right. Okay, such problems have been asked. Okay, and we can, this is a very simple problem, but it's easy to make a mistake. All right, it's very easy to make a mistake. So if you really think about it in a physical way, such problems, okay, it's probabilities are that you will avoid the mistake. Okay, you have to really imagine it. Okay, you have to really imagine. Whenever you can draw a diagram, you draw a diagram, and whenever you can imagine the physical situation, you just imagine it. Okay, and see what happens. If it's difficult, you go back to your train example always. Okay, trains are always helpful. It's really easy to imagine. So in this case, this pion is like a train. Okay, this pion is like a train. That's all. Okay. So there are more problems, but I think I'll just of the similar. You can just solve it in exactly similar manner. So I'll just put it in your notes. Okay, using these techniques. Okay. There's another problem in a slightly different manner that also I will do in the next class, and then we'll move on. Okay, and I'll give you more problems as exercises. If you have any questions, you can just ask. There's no point in doing so many problems of exactly the same kind. Okay, all right. There's one more kind of problems. There's this transverse velocity thing coming up, so we'll do that also in the next class, and then we'll continue. Okay. All right. Thank you. Are there any questions?
Thank you.
Thank you, sir.
Okay.